안녕하세요. 들리시죠? 안 들리나? 자, 빨리 시작하고 빨리 끊읍시다. 오늘은 뭐 남은 게 많진 않아서 지난 시간에 좀 많이 했으니까. 조금 렉이 있는데 잠깐만요. 왔다 갔다 하네요. Okay, let's start. So last time we talked about the series solution at ordinary point, where ordinary point is the analytic point of all coefficient functions. So when you investigate your ordinary point of second order differential equation, you need to set your first coefficient for the highest order term to be 1. Okay, so if you have something on the coefficient other than 1, then you have to divide each side so that it has of this form. Okay, so for example, if you have such a differential such as this form, then you can take any real number as ordinary point, because sine x and e to the x is analytic at every real number. So, and also we calculated one series solution at the 0 as ordinary point of this particular differential equation, and the method was to expand all the power series and then compare the coefficients. So we had this two equations. One is a particular equation to determine your coefficient of series solution, and the other is a recursive formula for those coefficients, and it gives some pattern of your coefficients, and depending on some unknown variable, and this unknown variable or parameter is determined by given initial value condition. So I also asked, now what if I have an initial value condition not at 0 but at 1? So if you had an initial value condition at 0, then your solution, this which has a parameter C1 and C2, can be made to a particular solution. Just plug in x equals to 0, because you have a power term which is x to the power. So if you plug in 0, then everything disappears except for the first few terms, and also same for the derivative of this solution. However, if you plug in 1, then the terms, this summation doesn't disappear, and your now to compute the actual limit of this infinite series, and most of times it's impossible to find the actual limit. Of course, you can find an approximate value of this limit using the MATLAB or other computing tool, but that's not the exact solution. That's not the exact answer. So we are going to expand at the different point. So that's our example today. So let's look at, okay, so here we have, let's look at the same differential equation. Y double prime xy equals to 0. But suppose that my initial value is given at x equals to 1. So for example, like this. So then I need to expand, I need to find my series solution at different ordinary point than 0 but 1. So let's say my y is given as an, which is coefficient, times x minus 1 to the power of n when n is 0 to infinity. So if you have such formula, then it assumes that this 1 is ordinary point of this differential equation, which is true because x, which is a polynomial, is analytic at every point. So 1 is obviously an analytic point of x, and other coefficients are 0. So every real number is ordinary point, analytic point. So let's try to do this step by step. So we have an. So when I take a derivative, first derivative, then the zeroth order, which is constant, disappears. So n start from 1, and n times x minus 1, n minus 1. So nothing changed, only my first term disappears. So I don't change the index here, okay? So I'm just taking derivative of these power terms. And y double prime now becomes the summation from n equals to 2, because when n equals to 1, the first term of y prime is constant, so it disappears on the second derivative. So we have an, n minus 1, x minus 1, n minus 2. Okay? And let's plug in into the differential equation. So n equals to 2 to infinity, an, n minus 1, x minus 1, n minus 2, plus. Now, you have x, but what happens when I just plug in x here? So this x makes trouble because everything is written on the power term, which is the x minus 1 to the power, right? But this x is not of the same form. So you cannot compare the coefficient if you keep this x. So I also need to expand this x as a power series in terms of minus 1 to the power. So obviously this is a polynomial, so any polynomial can be written as a power series, but that series is not an infinite series, but it's a finite series. Every polynomial, in other words, it can be written as finite power series, which is obviously Taylor polynomial. Okay. So when you think this is a Taylor series, the power series expansion is to find the Taylor series. But if you think about how to get the Taylor series, you take the infinitely many differentials of the original functions. You have a polynomial of fixed degree. Then if you take a n plus 1 derivative of the degree n polynomial, then it becomes 0, right? So Taylor series only has finite terms, and the finite sum of Taylor series is a Taylor polynomial. So your polynomial can always be written as a Taylor polynomial. So in other words, I can do this by my head, because this is so simple, so that I can write my sum, which is 1 plus x minus 1, which obviously becomes the Taylor polynomial of degree 1, and also it's equal to x. So I know that this is the Taylor series, Taylor polynomial. There's no other. There are only a unique power series expansion to any function. So let's plug in this one. So, okay, so let's try to make my index start from 0, because if you're looking at this y double prime series expansion, the index, the power of this term start from 0. So I want to write n to be the power, and let's write as index for the power here. So I'm replacing n minus 2 as n. Okay. So then, if I replace n minus 2 to n, then n becomes n plus 2, n plus 2, n plus 1, okay? And then this one becomes x minus 1 to the power of n. 유튜브 끊기는 건 제가 어떻게 할 수가 없어요. 자꾸 뭐 중간에 내가 뭘 해서 끊기는 게 아니라 학교 네트워크가 안 좋아서 끊기는 거라서. Okay. And plus 1 plus x minus 1. And then n0. So let's also distribute this too. So 1 times of this guy, n equals 0 to infinity, an x minus 1 to the power of n, and then multiply x minus 1. So we have n from 0 to infinity of an x minus 1 n plus 1 equals to 0. And again, so I just simply multiplied x minus 1 to this term, because I write x as a 1 plus x minus 1. This is 1 and this is x minus 1. And I had one more exponent here. So I want to make the form of power series all equal. So I don't want this n plus 1 appears here. So let's rewrite that. So we have n equals to 0 to infinity, a n plus 2, n plus 2, n plus 1, x minus 1 to the power of n. And so I write the second one again. So n equals to 0, infinity, an, x minus 1, n. And then the last one, if I write my exponent as n, now n starts from 1 instead of 0. So an, so because I'm replacing n plus 1 as n, okay, then n becomes n minus 1. So this is our formula. Minus 1 equals to 0. 좀 어떻게 할 수가 없어요. 학교 인터넷이 끊긴다니까요. 내가 할 수 있는 거는 여러분들이 못 들은 거 다시 얘기를 해줄게요. 지금 뭐 인터넷을 제가 학교에다가 뭐 새로 얘기를 할 수가 없잖아요. 끊겨서 안 들린 거 있으면 다시 얘기를 해주세요. 뭐 인터넷 불만은 제가 뭐 해결을 할 수가 없어요. 끊겨가지고 이해 못한 거 있으면 얘기를 해주세요. 비트레이트를 조금 내렸거든요. 화질이 조금 안 좋을 수도 있는데 봅시다 어떻게 되는지. 네, 그 부분 그럼 다시 할게요. 지금은 조금 안정적이긴 한데 so this part is okay. So I'm going to plug in this formula here and also y as here. Okay, so I have x here, still I have x. But I also want to expand my x at centered at 1 as a Taylor series. So this is the Taylor series of polynomial x. Okay. Why? You can just use the definition because if you take this as f of x, I'm taking a Taylor series at 1. So I'm taking f1, which is 1, and f prime of 1, which is also 1. But if you start taking a higher order derivative whose order is bigger than or equal to 2, then everything goes to 0. So we have only two non-zero coefficient of Taylor series. 지금은 좀 괜찮죠. 지금은 4메가bps로 떨어뜨리니까 좀 안 끊기는 것 같은데, 안정적인 것 같은데. So this is our coefficient, and if you plug into the formula of Taylor series, f of 1 plus f prime 1 divided by 1 factorial x minus 1, and the rest of the terms are all 0. So this is 1 and this is 1, so 1 plus x minus 1. So that's how I plug this part 1 plus x minus 1 to here, okay, and then expand this part. So first of all, I have summation 1 times of this series, okay, 1 times of this series, and also plus, so that's here, and then plus x minus 1 times this series, okay, that's this sum, okay. So that's why I get n plus 1, because I multiply x minus 1 here, okay. But my index here still is starting from n equals to 0 in these two. But then I want to make index represent the power of the power terms. Everything is okay except for the last sum. This sum, the power is index plus 1. So I replace that as n, and my index now start from 1 instead of 0, and index inside of this sum end is now becomes n minus 1, n becomes n minus 1. Okay? All right, so Yeah, so let's look at so if index of every sum start from the same number, that's fine. But we have two sums, first two sums index start from 0, and the last sum index start from 1. Okay? So then I cannot write recursive formula directly from this sum. I have to separate out first few terms until every sum start from the same number. Okay? So I collect when n equals to 0, which is the constant term. So when n equals to 0, then the non-zero term only appears in the first two sums. Okay, so first sum has n2 times 2 times 1, and this is x minus 1 to the 0, so there's nothing here. So n0, a0, and so this is the constant term, actually, the constant term of the left-hand side, and everything must be 0, so that must be also 0. So now, when n is bigger than or equals to 1, let's collect all the terms here. So we have n from 1 to infinity of n plus 2, n plus 2, n plus 1, x minus 1 to the power n. And then I can write with the same summand here, same sum notation, because also start from 1. So we have a n, and then here also we have a n minus 1 times x minus 1 to the power of n. And that must be 0. Okay? So this blue equation is equals to, so this blue equation is basically equals to this equation. So the constant term plus non-constant terms. So if you separate out the constant terms, then you can combine all these three sums into one big sums. Okay? But you have to separate the constant term because you don't have a constant term in the last summation. So now everything must be 0, so coefficient-wise, everything must be 0. So this constant term must be 0, and this sum must be 0. And then, if you select the coefficient of each exponent, that must be 0 too. So let's rewrite that. A n plus 2, n plus 2, n plus 1. I'm sorry, so I don't need this one. So it's included in the parentheses. Okay, and plus an plus an minus 1 equals to 0. Okay, so you have two equations. So let's delete this blue one. So one explicitly computes the value of a0 and a2. Well, there's only one equation, so you cannot find particular value for both parameter, but you know the relation between these two parameters. And the other one is a recursive formula, and this recursive formula only works for n is bigger than or equal to 1. But that's enough for finding the particular solution, because now let's try to find out first few coefficient of a. So a0 is a0. I really don't know what the value is, but a1 also is a1. But after a1, now a2 is equals to negative 1 over 2 a0 because of this first equation. And now let's look at the recursive formula. n plus 2 is equals to negative of 1 over n plus 2 n plus 1 times an minus 1 plus an. We have minus sign here because we pull this an plus an plus an minus 1 to the right hand side. So because of this recursive formula, we can compute A3. So A3 is now minus 3 times 2 times A2 plus A1. But we know what A2 is in terms of A0. So it's minus 1 over 2 A0 A1. Okay? So then this is 3 times 2 times 2 A0 minus 3 times 2 A1. Okay? How about A4? So A4 is minus 1 over 4 times 3 A3 plus A2. And we know what A3 is. This is our A3. And we know what A2 is. So let's write that. So this is equals to minus 4 times 3 of 1 over 3 times 2 times 2 A0 minus 1 over 3 times 2 A1 and A2, which is minus 1 over 2 A0. So if you combine all this, so this is 1 over 12 minus 1 over 2. So 5 over 12. So 5 over 4 times 3 times 12 0. And this one is plus 1 over 4 times 3 times 3 times A1. Okay. So if you are able to find a pattern of AN in terms of N, that's very good because you can expand your series solution infinitely many times. But many times it's hard to find the pattern of AN or exact formula of AN in terms of N. So we stop until we are satisfied to find the sufficiently large power terms. So I computed until A4, which means that I can expand my series solution until the degree 4 polynomial. And degree 4 polynomial usually is good for approximation. Well, in real situation, maybe it's not enough, but suppose that we are okay with the degree 4 polynomial, Taylor polynomial of a power series. So then let's try to write that. Write my series solution explicitly as y now equals to, so A0, A1, x minus 1, A2, x minus 2, A3, x minus 3, A4, it's 1, 2, 3, 1 square, 1 cube, 1 fourth, and so on. It goes infinite, but I know that my coefficient up to A4, so that's why I wrote only A4. So A0, A1, x minus 1, and A2 is minus 1 over 2, A0, x minus 1 square, and A3 is 1 over 12, A0 minus 1 over 6, A1, x minus 1, 3. 지금 또 끊기네. 지금 보니까. So, and then, okay, A3, A4, what's A4? Here, 12, 5 over 144, A0, and 12, 6. So 1 over 72, A1, x minus 1 fourth. Okay. So this is a messy expression. I want to make sum of two fundamental solutions. So A0 and A1 are unknown variable, which is a parameter, and that serves as a parameter in the general solution of our series solutions. So let's combine A0, a term that which contains A0. So we have 1 minus 1 over 2 x minus 1 square and 1 over 12 x minus 1 cube, and here we have 5 over 144 x minus 1/4, and goes on, but we didn't compute it. So A1 x minus 1 minus 1 over 6 x minus 1 cube and 1 over 72 x minus 1/4, and so on. So this series is a series expansion of one particular solution to this differential equation. Okay. Since we expressed our general solution as series solution, this is the series expansion of our particular solution. And also this is another particular solution, y2. y1, y2 are fundamental solutions to these differential equations. Now let's plug in our initial value condition where y1 equals to 1 and y prime 1 equals to 0. So when I plug in y1 equals to 1, then everything goes to 0 except for 1 here, and this all goes to 0. So it means that A0 is 1, right? And what happens to I plug in y prime equals to 1, y prime 1 equals to 0? If I take a derivative of x on these terms, constant term disappears, and this becomes the degree 1 polynomial, and this one becomes 1, and everything is the degree higher than 1. Therefore, A1 only survives. So A1 equals to 0. So what's the answer? Answer to the differential equation satisfying this initial value condition is y equals to this y1. And we know that y1 exists, but there's no other way to express y1 other than this series expansion. So we can only approximate the graph of this solution y1 using the Taylor series. So 1 over 12 x minus 1 cube and so on, 1 over 144 x minus 1/4, and so on. And in practice, when you try to graph the function, then you have to use P4 of your solution y1. But that's okay. So we had a series solution centered at 1 because we had an initial value at 1. Okay. You could have done this with series solution centered at 0, but it's impossible to find the actual formula or actual power series expansion. This is a legitimate way to find your series solution with given initial value condition. If there is no initial value condition given, then you can choose your center freely as any ordinary point. In actual problem, the problem will ask you to find a series solutions and centered at particular ordinary point. Okay, so you have to worry about which ordinary point you have to choose. So let's look at another example. So if you have any questions, please stop me anytime. Here is a question. So you have initial value problem of this form, and now this y double prime has coefficient x. So this is not the correct form to check whether the point is ordinary point or not. So you have to divide x on both sides, so you get this differential equation. Now this becomes q and this becomes r. R and p, so p is a zero function, so constant zero function, and r is also constant function. So these functions are analytic at any real number. However, if you look at q is discontinuous at 0 and also it diverges at 0, and 0 is the only non-analytic point. Okay? So you choose the ordinary point other than 0 because 0 is the only non-ordinary point. So let's suppose that we took 1 as an ordinary point and we want to find the series solution at 1. Okay? So let's try to compute the series solution again. So I'm going to explain how we arrive to this recursive formula with these particular equations. It's a long computation, so if you have any question at any time, or if you miss the computation because of lag, please stop me anytime. So we have y double prime plus 1 over xy equals to minus 1. Now I'm using this as my series solution. So 1 over x must also be written in terms of series solution, series expansion at 1. So I also need my 1 over x something in terms of x minus 1 to the power of n with some coefficient here, because that's how I can combine. In that way, I can combine these series, power series centered at 1. So when you have such formula or such function, easy way is just simplest way, not easy way, but simplest way is simply take the Taylor series definition and plug into the numbers. You have a function and you have a derivative and you just plug in. Easy way is, or tricky way is to use this kind of formula. So you have 1 plus 1 minus x as x. So you can rewrite your function 1 over x as this formula, and then this is 1 minus 1 minus x minus 1. Therefore, you can use geometric series, which is n equals to 0 to infinity of minus x minus 1 to the power of n. So therefore, this is minus 1 to the power of n times x minus 1 to the power of n. N equals to 0 to infinity. Okay. And let's plug into the formula. Let's erase this. So y double prime becomes n equals to 2 to infinity of an n plus n times n minus 1 times x minus 1 to the power of n minus 2 and plus so okay, in this way it's very hard, so I'm going to use a different way. Finish off this method is not finish off this method and show this is not a efficient way of computing the series solution, and then try to plug in this one. So n equals to 0 to infinity minus 1 to the power of n x minus 1 to the power of n times, So these times, this is the 1 over x. Okay, so this whole thing is 1 over x times n equals to 0 to infinity of a n x minus 1 to the power of n. And that must be equals to negative 1. Whole thing must be equals to negative 1. So the first sum, now if you rearrange, reindex your n, now exponent start from 0, so this is a n plus 2, n plus 2, n plus 1, x minus 1 to the power of n. And let's look at the product of two series. So this is 1 minus x minus 1 plus x minus 1 squared, and so on, times a0, a1, x minus 1 plus, and so on. So you have to use the product of two series. So the smallest degree comes from a0, right? And then degree 1 term comes from multiplying 1 with a1 and minus 1 to a0. So this is a1 minus a0, x minus 1, and so on. So you have to compute the series using this kind of recursive formula, but it's easy until you have degree 1. But if you keep moving, keep increasing your degree, the formula gets really messy. So it's very hard to combine these two formula in a big one summation. You have a summation and some summation of summation. So I'm not going to use this one to plug in this 1 over x with this geometric series. For example, so this one, so the general formula has very messy expression. So we're not going to use this. Not efficient. Let's try to use the original formula, which is x times y double prime plus y equals to minus x. Okay, or you can just go back to really original formula, that's equals to 0. Use this one. So we only divided x in order to find out the ordinary point. Once you find the ordinary point, find a series solution, you can just simply use the same formula, original formula here. So let's try to write my x as a series expansion at 1. So that means 1 plus x minus 1 times y double prime, which is n equals to 0 to infinity. I use 0 instead of 2. So a plus 2, n plus 2, n plus 1, x minus 1 to the power of n, and plus y, n from 0 to infinity of an, x minus 1 n, and then x, which is 1 plus x minus 1, and that equals to 0. So let's rewrite this. So first sum end, start from n equals to 0, because 1 times this sum. an plus 2, an plus 2, an plus 1, x minus 1, n. Second sum, start from n equals to 1. So then I have to replace n with n minus 1, n plus 1 as n, and n with n minus 1. So now it becomes an plus 1, n plus 1, n times x minus 1 to the power of n. How about the third one? So this one is n from 0 to infinity of a n x minus 1 to the power of n. Now this one is, it's a summation of two terms. This is n equals to 0 and this is n equals to 1, right? So this, we have four summations, 1, 2, 3, and 4. So, and it all start from different locations. So this one start from 0, 1, 0, and 1, 0. This comes separately. So you have to separate your 0 terms, 0 degree terms, and 1 degree 1 terms, and the rest of the terms. So let's look at the degree 0 term. When n equals to 0, here is the 0 term, the constant term, which is a2, 2, 1, and constant. And there's no degree 0 terms here. And here we have 0 degree plus a0. And here we have degree 0, which is 1, so plus 1. And that must be 0. That's the constant term. And the right-hand side is all 0. So when n equals to 1, then this is a3, 3, 2 times x minus 1 to the power 1, but I'm only comparing the coefficients, so let's skip that. Then also there is an n1, which is the first term, so which is a2, 2, 1, okay? And how about this? We have n equals to 1 survived as a1, and here we have the first term has coefficient 1, so this was plus 1. So now, when n is bigger than or equal to 2, there's nothing here. Then all the terms here can be combined together because there are degree 2 or higher terms in these three summations. So n equals to 2. So when n is from 2 to infinity, let's combine all the summations. A n plus 2, n plus 2, n plus 1, plus a n plus 1, n plus 1, n, and a n, x minus 1, n. And that's 0. Okay? So that means this term is 0. A n plus 2, n plus 2, n plus 1, a n plus 1, n plus 1, n plus a n equals to 0. And this recursive formula only works for n bigger than equals to 2. Okay? So let's look at the first terms. So we don't know what a0, a1 is, but we know what a2 is because of the first equation, which is minus 1 over 2 a0. And how about what a3? Now I know what a3 is because of this formula. This is minus 1 over 6, 1 plus a1, we don't know what a1 is, and plus 2a2, and I know what 2a2 is. This is minus a0. Minus a0, right? And from a4, I have to use the recursive formula. So this formula says that a n plus 2 equals to minus n plus 2 and a n plus 1 minus 1 over n plus 2, n plus 1, a. So a4 is now minus 2 over 4 times a3 minus 1 over 4, 3, a2. Okay. Now I know what a3 is because of the previous computation. We have minus 1 over 2 times minus 1 over 6, 1 plus a1 minus a0. And I know what a2 is. It's minus 1 over 2 times minus 1 over 2 a0. So if you make it simpler, this is 1 over 12, and a0 we have 1 over 24, and minus 1 over 12. So this is minus 1 over 24, A0. And if you combine A1, this is 1 over 12, and that's 1 over 12. So 1 over 12, A1. So that's A3, A4, expressed in terms of A0 and A1. You can keep doing this until you're satisfied, or in the problem satisfied. Then let's combine everything. Our original formula for y can be written as A0 plus A1 times x minus 1, and A2, which is minus 1 over 2 A0 x minus 1 square, and A3, which is minus 1 over 6. Let's, okay, so minus 1 over 6 minus A1 over 6 plus A0 over 6 times x minus 1 cube. And then A4, which is 1 over 12 minus 1 over 24 plus 1 over 12, A0, A1, x minus 1/4, and so on. And then let's combine A0 and A1, and then separate out the term which doesn't contain A0 or A1. So A0, combining A0, we have 1 and minus 1 over 2 times x minus 1 square. And here we have minus 1 over 6 x minus 1 cube. Here we have minus 1 over 24 x minus 1/4, and so on. And let's combine A1 term. We have x minus 1, and here we have 1 over 6 x minus 1 cube. Here we have 1 over 12 x minus 1/4, and so on. And it's different from the previous example. So previous example only had a solution which is a linear combination of A0 times the fundamental solution plus A1 times fundamental solution. But here we have another term which doesn't contain A0 or A1. And if I combine those terms, I have minus 1 over 6 x minus 1 cube and plus 1 over 12 x minus 4th, and so on. So this is a general solution. This is a general solution. What's the first part? So this is, let's say, y1, and let's say this is y2, and say that this is yp. So we have three sets of solutions written in terms of series expansion. y1 and y2 are fundamental solutions to homogeneous differential equation. So we had y, x, y double prime plus y equals to negative x, right? So you can separate out this yc double prime yc equals to 0 and yp prime plus yp equals to negative x. So then this y is yc plus yp. So that's the principle of superposition that we talked about a long time ago. Is it the computation wrong? A2가 1 over 12 minus 1 over 2? 지워버려가지고 모르겠네. 잠깐만요. A2, wait. 2 minus 1 over 2. Right, you're right. So the computation gets wrong here. So I have to replace this as minus 1 over 2 x minus 1 square. Well, you know what I'm saying, so need check. So check here. So check every coefficient here. Okay. So check everything again. So we have a general solution as a sum of complementary solution and particular solution. So these first two summand serves as a complementary solution. This y1, y2 here are fundamental solution to this one, the first equation. Okay? So the first one, let's say this is the second one. Okay? The second one is the original differential equation. And yp, which doesn't consist of any parameter here, this is the particular solution to the given original non-homogeneous differential equation. Is particular solution to original differential equation, non-homogeneous one. So this is homogeneous, and this is non-homogeneous differential equation. Okay, but everything is written in terms of series solution. So thank you for the correction, and you have to check this coefficient again because I messed up with the A2, so everything is now messed up. So you have to compute this coefficient again for the correct formula here. Okay. Oh, by the way, yeah, n equals, yeah. All right. Yeah, here is I think this is the correct one. So these coefficients are correct formulas. So maybe I'm not that too wrong. So it's minus 1 over 12. So it's a little bit different, right? So plus, minus. So yeah, well, you get the slide here. Okay. So suppose that you have an initial value condition at 1, then you can simply plug in 1 to find out A0 and A1. So and then you can write your particular solution in terms of one solution, one series solution. Okay. So now the important part is that the radius of convergence can be computed if you know the series, power series. But here, this power series has no general formula for the coefficient. You have a particular coefficient for small degrees, but the general solution, general form of this coefficient cannot be written in terms of n, right? But how do you know the radius of convergence is 1? Because in the beginning of the differential equation, we had 0 as non-analytic point. And your solution, which expanded at 1, cannot pass through that non-analytic point. So you are centered at 1, and you cannot pass the non-analytic point 0. So that's the farthest you can go from the center 1. So therefore, the radius is 1. So without explicitly knowing your coefficient of series solution, you can find out that the series solution, the radius of convergence of series solution of your solution. And then that means that if you want to approximate your solution with first few terms of this power series, it only works until your x is between 0 because the radius of convergence is 1 and you're centered at 1. Okay, and also it's going to be diverge or going to be behave weird way if your x approaches to 0, because 0 is the point where your coefficient function 1 over x diverges. So you might expect that this also behaves in weird way or diverging, such as diverging behavior when x approaches to 0. So it's important to use this series solution only when it's very close to 1, okay? And even if you want to extend your range centered at 1, it's important not to go beyond this radius of convergence. So any questions? So far, any questions? So let me emphasize again. So we only have about 28 students. So I'm giving you some incentive for the final. So I'm going to write that in the chat in LMS. So, okay, so key point. Find this. So finding series solution is one of the key point. I'm not going to tell you the second one. I'm writing on a chat board here. Okay. So the thing that I wrote in the chat board is what I already said in the previous minutes. Okay, so we're going to move on to the regular singular point. So this is a very long computation. This is somewhat somewhat inconsistent with our content here, but it's okay. So what we are trying to do in this regular singular point is we are trying to find a singular solution. Okay, so in a way that it's a singular solution, and it's not trying to find the solution to the initial value problem. I'm simply trying to find a solution that works near a singular point, but not at the singular point. Okay, you will see what it means at the end. So suppose that we have a second order differential equation of this form, and then suppose that C is a singular solution, which means that PQ is non-analytic at C, okay? And we have a homogeneous differential equation. Now, although C is non-ordinary point, if these two functions where this px times x minus c and qx times x minus c squared are analytic at c, then we call this c an regular singular point. So it's a singular point, but among the singular point, it's still a regularity in this singular point. So for example, these function, the first function has 0 as regular singular point, because if I rewrite this as y double prime minus 3 2x y prime minus 3 plus x over 2x squared y equals to 0. So this is p, minus 3 over 2x, this is p, and this is q. If I write x times p, it's minus 3 over 2, which is analytic at 0. And if I write x squared q, then this is minus 3 plus x over 2, which is also analytic because it's polynomial. Therefore, 0 is regular singular point to this first differential equation. How about the second? We have y double prime 1 over xy prime 1 over xy equals to 0. So if I take xp, then this is 1, and x squared q, this is x, and 1 and x are both analytic at 0, so therefore 0 is also regular singular point to the second equation. And it's obvious that it's a singular point, it's not an ordinary point, because these pq here and here all have non-analytic point at 0. 0 is not even defined, it's diverging near 0. And also, if you're looking at these two equations, this is not a solvable equation using Euler formula, Euler characteristic, right? So in order to use the Euler characteristic, you need to have an exponent of x equals to the order of the derivative of y. For every terms, we have degree 1 and order 2, and degree 0, order 1, degree 0, order 0. So you cannot solve this equation using Euler characteristic. Okay? So let's try to find a solution using Frobenius method. It's a simple method. We're trying to find a solution of this form where in the exponent we have some additive term. We have n plus r. So our goal is to find an satisfying differential equation, also r satisfying this differential equation. So trying to find this solution to this differential equation, for example, at x equals to 0. So luckily I have a slide here, so it's important. So take a careful look at this slide after the class. So let's try to start from y equals to an x plus r. So if this 0 were ordinary point, we don't need r, okay? But this is a non-ordinary point and it's a regular singular point, so I need r. I need to find non-zero r. So plug in this for y double prime and y here. So I'm going to make the exponent of x inside of this summand as similar as possible. So we had x to the n plus r minus 2 in the first summand here, and I'm trying to make it as a n plus r, okay? Using by replacing. So there's okay. So there's missing lots of missing computation here. So it might hard to follow from this first equation to second equation. So let me write that in the board. Okay. So, okay. So I'm not going to explain why I get the y double prime solution as expansion as this form. It's already explained in the previous examples. So we have 2x squared n from 0 to infinity an n plus r n plus r minus 1 x to the power n plus r minus 2 minus 3x and 0 an n plus r x n plus r minus 1 minus 3 plus x n equals to 0 to infinity of an x n plus r. And let's try to make everything in terms of n plus r. Okay, so I'm going to replace r minus 2 with r. Okay, so then okay, so first one I don't need to actually replace that because I have x squared, so I'm going to plug in squared. I combine x squared to x to the n plus r minus 2. So I get this to, for the first sum end, we have 2an n plus r minus 1 x to the n plus r. Okay, so plus 2 cancels out. And how about this? The second sum end? We have minus 3 times 1 minus 1. So we have an n plus r x to the n plus r, where n from 0 to infinity. And here we have minus, let's split this, 3 times an x n plus r, n from 0 to infinity, minus n from 0 to infinity of an x n plus r plus 1. Okay? So for the first 3 terms, I can combine these terms. Okay? So that's how I get the second equation in the slide. So we have n from 0 to infinity of coefficient combined 2an n plus r minus 1 minus 3an n plus r, and then minus 3an x n plus r, and then minus n from 0 to infinity of an x n plus r minus 1. Now, I also want to combine these to sum end, these to summation. But this one has a start point as r. When n equals to 0, it starts from r. But here, when n equals to 0, it starts from r minus 1. So if you want to match these two, I have to split this second sum end as n from 1 to infinity and when n equals to 0. So when n equals to 0, so we have n r minus 1. Okay. So then I can rewrite this sum. So now when it starts from n equals to 1, that's when exponent is n plus r. That's when exponent is r. So I can replace n minus 1 as n. So then it starts from n plus r, but now I replace n minus 1 as n. So n becomes n plus 1. Okay? This kind of change of index is very useful and also important when you compute the series solution, not to mess up with the formula. So then now we can combine these to sum end. So now becomes n from 0 to infinity of 2a. Let's combine these. So we have a n times 2n plus r, n plus r minus 1, minus 3 n plus r minus 3. So that's a coefficient for an. How about inside? We have minus an plus 1 and times x to the n plus r and minus a0 x to the r minus 1. And we want, that's the left-hand side of the differential equation, that we want this to be 0. Okay. All right. So oh, there's a typo. There's a typo in here. There's something wrong. They're trying to compute this. So n plus r minus 1. Okay, let's try to compute this. So let's keep doing this. It goes to infinity, an. I'm trying to make this part simpler. So this is n plus r, 2n plus 2r minus 2 minus 3 minus 3. I'm sorry, so I think I messed up with some computation. So okay. It's plus 1, yes, and then okay, so I messed up here, sorry. So yeah, let me just rewrite this. So this one was what? This one was this one, right? So when n equals to 0, it's not r minus 1, I'm sorry. So this is not r minus 1. This is r plus 1. So r plus 1. So, and then now we start from 0. 0? No, it's not from 0. So it's equals to n equals to 1. So now you start from 1. So let's try to so this is n minus 1. So when n equals to 0, the term is a0 times x to the r plus 1. So this is the term when n equals to 0. So when n is 1, this is a1 times x to the r plus 2, right? But in that case, so let me go back to the original definition here. So n from 1 to r plus 1 here. Okay. So n from 1. Oh, by the way, so I'm sorry, so I don't need this. Sorry for confusion. So I combined all this and I had n from 0 to infinity of an x to the n plus r plus 1. So then I'm going to replace n plus 1 as n, okay? So when n from 0 to infinity, n plus 1 is from 1 to infinity, right? So if I replace n plus 1 to n, then n is now from 1 to infinity, and then original n now becomes n minus 1, right? This is the right formula, okay? So now let's compare these two sum end. The exponents are the same. Here we have exponent n plus r, but the starting point is different. This starts from n equals to 0, and this starts from n equals to 1. So I'm going to take the first term when n equals to 1 of the first sum end out, and then combine the rest of the terms when n is bigger than or equal to 1 as the one sum end. So when n equals to 0, we have 2a0, 0 plus r. So that's important. So we have n equals to 0 plus r minus 1 minus 3a0 times 0 plus r minus 3a0 as coefficient for x to the r, and then big sum end from n equals to 1 to infinity of this thing. So an 2n plus r n plus r minus 1 minus 3 n plus r minus 3, and then that's the coefficient for, right? Coefficient for xan plus r, and then minus an minus 1 times x to the n plus r. Okay. So I want this to be 0. Whole thing must be 0. So therefore, this part must be 0, and for any n, this thing must be 0. So let's compute the first one. So this is the particular one equation. So we have 2a0. So we have a0 everywhere. So a0 can be taken out, right? So 2 times r minus 1 minus 3 times r minus 3 must be 0. So this is 2r squared minus 2r minus 3r minus 3. And this is 2r squared minus 5r minus 3. Is it right? Yeah. So it's a 1, 2, 1, 3, 3, 2 minus 3, 1. So then this is r minus 3, 2r plus 1 equals to 0. So in order to have 0 on the first coefficient, your r must be either 3 or minus 1 over 2. Okay, we have a candidate for r. How about the second? So this is a recursive formula, only works for n bigger than or equal to 1. And let's simplify that formula. We have an times n plus r, 2n, 2r, minus 2, minus 3, minus 3, minus an minus 1 equals to 0. And this is an see, 2 times an plus r squared minus 5n plus r minus 3 minus an minus 1 equals to 0. So therefore this is same equation actually. So we have 1, 2 minus 3, 1. So n plus r minus 3, 2n plus 2r plus 1 times an. Raise this. Minus an minus 1 equals to 0. Okay. All right, here's now the final result. So we have two cases when r is equal to 3 or minus 1 over 2. So let's try to investigate each cases. So when r is 3, so that's the one case, our recursive formula becomes an times n times 2n plus 7 equals to an minus 1. So in other words, an is equals to an minus 1 over n 2n plus 7, right? So when nr equals, so let's try to compute this case. A0 is unknown A0, so we don't know what A0 is. But since this recursive formula determines the consecutive term from the previous term, so A1 is now 1 times 9A0, and A2 is now 2 times 2, 11 over A1, but A1 is also 1 over 1 times 9 of A0, and so on. So therefore, when r is equals to 3, I know that my solution y is written as A0 plus A1, which is A0 over 9 x to the power 1 plus 3. Because in our original setup for y, we had x to the power of n plus r, right? So r is now 3. So when n equals to 1, then the power of x is 4 instead of 1, okay? Then A2, which is 1 over 2 times 11 times 9 of x to the power 2 plus 3. I'm sorry, so A0 also has a coefficient. A0 has a x to the 0 plus 3, so x3, okay? And so on, it goes on like this. So this is the one solution when r equals to 3. And when r equals to minus 1 over 2, then our solution now looks like y equals to A0 x to the minus 1 over 2 plus A1 times x to the 1 minus 1 over 2, A2 x2 minus 1 over 2, and so on. But the recursive formula says when r is negative 1 over 2, an times n plus minus 1 over 2 minus 1 over 2 minus 3 times 2n 0, so this is just 2n, equals to an minus 1. So an is now become n minus 1 over, this is 7 over 2 times 2n an minus 1. For simplicity, we had 2n minus 7 times 2n 2an minus 1. So that's the recursive formula when r is negative 1 over 2. So therefore, we have A0 is A0, x to the negative 1 over 2. A1 is now, when I plug in 1 here. This is minus 5 times 2 to a0 x to the power of 1 over 2. How about a2? Then I plug in 2 here. We have minus 3 times, so by the way, so I don't need 2 here, so I just delete 2. So when I plug in n equals to 2, minus 3, and 2 to a1, but I know what a1 is, so that's 1 over minus 5, a0 x to the power of 3 over 2, and so on, right? So we have two solutions. So let's say this is y1 and this is y2. What happens when we have two solutions to homogeneous differential equation? We just add them together and then multiply the parameter. But the parameter is already here. So a0 is undetermined here, but also a0 undetermined here. But a0 here and there are different. But a0 is just the unknown parameter. You can plug in any number for a0 so that this equation is a solution to the differential equation. So when you combine these two solutions as a general solution, you need to use different parameter for this type of solution and this type of solution. So for example, let's say C0 times, let's replace A0 as C0 in this solution. We have x cubed plus 1 over 9 x fourth plus 1 over 2 times 11 times 9. I might do this computation, but just you can look at the slide for the actual value here. So x fifths here, and then let's use another parameter different from C0. Let's say C1, and then replace A0 with C1 here. So get x to the minus 1 over 2 and minus 1 over 5, x 1 over 2, and here 3, 2, 5, x 3 over 2, and so on. So you have a set of two solutions, and combining the linear combination becomes a general solution. This is the general solution. But as I said, this Frobenius method is not trying to find the solution which is analytic at 0. Look at this one. So we have 1 over x to the 1 over 2. So basically our term contains 1 over square root of x. This one is not analytic. Not analytic at 0. So this Frobenius method is not trying to find a solution which is analytic at 0, or nor we can find a value at 0. You cannot find C0, C1. You cannot find C0, C1 with the initial value condition y0, let's say y0 and y prime 0 as y1. It simply doesn't make sense. If your initial value is given at 0, it's impossible to find C0 and C1 by plugging x equals to 0. So finding the series solution using Frobenius method is not trying to find the particular solution to this differential equation at this regular singular point. What we are doing is Frobenius method, using Frobenius method, is trying to look at the series solution expansion slightly outside of the regular singular point. Let me write that. Frobenius method is to find a series solution expansion of the solution slightly outside of the regular singular point. So for example, if you have we had 0 as a regular singular point, the solution, our solution, is not defined at 0. It's impossible to draw the solution near 0. It's diverging. So what we're trying to find is somewhere outside 0, right here, minus from epsilon to epsilon, trying to find the graph or approximate value of the solution outside of this regular singular point. So this is the domain of interest. Not trying to look at what happens at the regular singular point. I'm trying to look at what happens outside of the singular point, but not too far outside of singular point. Just right, just near 0, but not actual 0. Okay, that's the whole goal of this Frobenius method. And I think another section of our course may not contain this part. The other sections of our class doesn't cover this Frobenius method, because I understand why they don't cover it, because this method is quite different from it's not consistent with what we are trying to do so far. What we are trying to do is find the analytic solution, which makes sense at that point, which makes sense to find the graph or find the value near the point of interest. But the Frobenius method, as I emphasized again, is not trying to find the value or graph near the point of interest. We are trying to find the value or approximate graph of the solution outside of the point, okay? Because it's impossible to draw the graph at that point. So what we can do is just see what happens outside at that point. So it's a little bit different concept, different feeling of finding the solution in Frobenius method. So anyway, this is the one way you can find another solution. And there's a few more computation if you look at more slide, that we found R. We found R with the Frobenius method, but sometimes your R could be a double root, or if R happens to be 2 integer roots, then sometimes this y1 and y2 becomes exactly the same solution, same series solution. What happens in that case is using the reduction of order. And using reduction of order for the series expansion requires the series division and series multiplication. So it's get really complicated. So I'm not going to cover that here. We don't have time, and also there's no point of doing that in our hand. So we are going to finish here for the series solution. So any questions? Okay, if there are no questions, thanks for listening. Have a good lunch, and hope you have a safe trip to DGIST, because we are going to have so you're going to come back to the school on this weekend, right? So I hope you see on the final, and if you have any question in between, week 13 and 14. Let me know. Okay. Let me know by email, or you can arrange a meeting, offline meeting by email. 일단 끝났고요. 제가 녹화를 따로 하고 올리는 게 아니기 때문에 유튜브 방송 그대로 아마 나갈 거예요. 그래서 뭐 방송 나갈 때 방송 한 개 끊겼으면 아마 영상도 끊길 거예요. 일단 뭐 확실치는 않은데 한번 보세요. 어떻게 작동할지는. 질문 있으면은 이메일로 하시고, 그러니까 중간에 이제 그 설명 안 되는 부분이 있으면, 그러니까 끊겨가지고 못 들은 부분이 있으면 다음 주에 학교 오시니까 오프라인 오피스 아워 신청하시고 이메일로, 그러면 다시 설명해 드릴게요. 자, 오늘 고생하셨고요. 다음 주에는 라플라스 합니다.